We're going to talk about improper integral. Now, let's take a look at this. What is the graph for 1 over x squared? Anybody remember? How does it look like? This is actually in one of the dance moves that I gave you guys. Okay. So 1 over x squared looks like this. So when x here is positive, then the graph look like this. Now this is an even function. So it's going to be symmetric with respect to the y-axis. So on the other side, we also have this one over here, symmetric, this. Okay. So this is the graph for 1 over x squared. Now today, we are trying to find the area between 1 and t, and they stay positive. What will be this area under the curve? This area over here, according to what we learned about area under the curve, right? What was the formula? It's the integral of this function, right? The function here is 1 over x squared, and x go from 1 to t. So 1 to t over here. Now, after that, we can evaluate this integral. Antiderivative 1 over x squared over here it is. What is the antiderivative 1 over x squared?
Negative 1 over x.
Yes, you got it. Good job. Okay, negative 1 over x. Now, over here, x go from 1 to t. So we're going to get negative 1 over t minus negative 1. So that is going to turn out to be 1 minus 1 over t, right? Now, this is the area under the curve on this first quadrant, right? When x go from 1 to t. Now, we're going to take this t and move it, okay? As we're going to move it and going to infinity. So basically, we're trying to find the area under the curve from 1 on over here, underneath this curve, okay? So what would this be? Okay, now this is start from 1, and then we're going to let the t here go to infinity. T go to infinity. So trying to find this area under the curve. So what will be this area under the curve? Now just like before, we can express this area under the curve, just like the one up here. So that will be 1 over x squared. This integral 1 over x squared, x go from 1. And then now the upper limit here, we have this infinity right here, okay?
Actually, let's see.
So this is one example of an improper integral, okay? When you have this upper or lower limit here in infinity or negative infinity, so this is an improper integral. But over here, you can try to think about that, represent this area under this curve right here. This improper integral here is defined to be the limit of this proper integral, where x here go from 1 to t. And then you take this proper integral over here and take this t go to infinity. So this improper integral here is defined to be the limit of this proper integral, where this upper limit here go to positive infinity. We have done this proper integral up here, right? The result it is 1 minus 1 over t. So we're going to take this limit, 1 minus 1 over t, where t go to infinity. So we take the limit of this proper integral, okay? Now when t go to infinity, what does 1 over t goes to?
0.
So this part over here go to 0, okay? So this whole limit here will be equal to 1, right? So this is kind of interesting. Now over here, this one extends forever, right? And the area under this curve, okay, is actually equal to 1. Imagine you have the strip continue forever, but it has a finite area here to be 1. Okay, so what you have seen over here, it is one example of an improper integral, this one over here, okay? When the upper limit here or the lower limit involve infinity or negative infinity, that's called improper integral, and it's a type 1, okay? So let me write it down. So this is improper. When the upper limit or the lower limit here involve infinity or negative infinity, this is the improper integral of type 1. So as you can see, this is called type 1. So we must have another type, right? Type 2 coming. Okay. Question? Okay. So what happened over here? Now we have this definition. So this integral, say the upper limit here is infinity, then we're going to define it this way. That is going to be the limit of this proper integral. We place this infinity here by t, and then let t go to infinity, providing that this integral exists for every t greater than or equal to this a. So if this integral here exists for every t greater than or equal to a, you take this limit as t go to infinity, that will be equal to this improper integral over here. Now what happens if the lower limit here it is infinity? So how would you like to define that? You can define that as the limit of this proper integral, and we place this negative infinity here by t, and let t go to negative infinity, right? Providing this part right here, okay, providing this, and then providing this. Providing this part, this integral, this proper integral exists for every t less than or equal to a. So the t here is less than or equal to this a. Okay. Now, so we're going to define those improper integral this way. So we place the infinity by t. Okay. So those will define to be the limit of proper integral. So improper integral defined as the limit of proper integral. Question? Now over here, if those limit over here, okay, if the limit here exists, then we call those integral over here, the integral here, convergent. If the limit exists, then we say this integral convergent. Okay, the integral over here, what are the integral? These two. Okay, so these two integral over here, we call them convergent. Is convergent. Is that a movie called Convergent or Convergence? Did I watch that? If the limit over here exists as a real number, then we say this integral will be convergent. Convergent in Chinese, we call that Sonian. Now, what happens if the limit does not exist? What happens if the limit over here does not exist as a real number? Maybe it's infinity. Then we say the integral over here is divergent. Divergent in Chinese will be opposite with the convergent right here. So some people will say 不收年. Actually, in 不收年 in Chinese has a different meaning. It was kind of funny, okay, if you know the Chinese. It's actually, we call that 发散. Okay, so this is convergent, and then this is divergent. So the limit here is a real number, then convergent, and this limit here, if it's not a real number, then it's divergent. Okay, so some of you will say that, what happens if the upper and lower limit here, it has infinity and negative infinity? So how would you like to define this? So first, we're going to break it into two parts. The first integral here will go from negative infinity and go to a, and then here will from a go to positive infinity. So break it down into two improper integral over here. The a over here, usually we make it 0. So once you break it into this two part right here, then this part here, you can use this definition, right? This one use this definition. This one here will use this definition. Okay, now this improper integral over here, it is convergent, providing that both this integral and this integral are convergent. So this integral here is convergent if and only if both this integral and this integral are convergent. Now, what does it mean? That means if one of them, this two integral here, if one of them diverge, then the sum over here is going to be divergent. Question over here? So to be precise, so I'm going to give you this example. So for example, if this integral over here diverge to negative infinity, and then the other integral over here diverge to positive infinity, then we don't say they cancel out, okay? And then we'll say this is going to be divergent, okay? So the whole thing here will be divergent. So if you want to visualize it, for example, suppose you have this right here. Say this area here diverge to infinity and this diverge to negative infinity, and then you don't cancel them out. And then you will say that that integral will be divergent. Okay, so take a look at this one. Now we're taking the integral of 1 over x. X go from 1 to infinity. That is very similar to the one that we have done. This is 1 over x. We know how the graph look like, right? Okay, so we remember the dance move. So 1 over x, the graph is going to be at the first quadrant, the graph is going to be like this. That's 1 over x. Okay. And now we're trying to find this integral 1 over x, x go from 1 to infinity. So again, it's trying to find this area under the curve when x go from 1 to infinity. So that's kind of similar to the one that we have done for 1 over x squared. So we're going to use the definition. This is an improper integral. So we're going to define this as the limit of this proper integral. We place infinity here by t, and then let t go to infinity. What's untitled t? 1 over x with respect to x. That is...
Is it natural log?
Yes.
ln x?
Good. Natural log of absolute value of x, right? You got it. Good job. Okay. And then x over here go from 1 to t. Okay, so remember this x go from 1 to t, which is going to be equal to, let t go to infinity, ln of absolute value of t minus ln of 1. Well, we know ln of 1, it is what? Equal to 0, right? Equal to 0. So we're taking the limit of ln of t, where t go to infinity. As t go to infinity, ln of t also go to infinity. So this limit over here will be equal to infinity. So that's infinity over here, which is not a real number. So because the limit over here does not exist as a real number, right? So what do we say about this integral? Convergent or divergent? So we'll say this integral over here will be divergent.
Divergent.
All right, so we will say this integral over here, we say that is divergent. Okay, now you might ask, they are so similar, right? So let's put them together. Now we have two functions. One is 1 over x squared. The other one it is 1 over x. The graphs are very similar. So we'll have this, and then this one over here. Okay, notice that they are very similar, right? However, when x increase, x squared is going to increase much faster than x. So this is going to go closer to 0 faster than this. Okay, so now we have this from 1 to infinity. Let's think about the area under the curve. What's this area under the curve? We just found this. It is, what's the area under the curve?
1.
It is 1, right? So we found that to be 1. So the area over here under the curve is equal to 1. Now what about this part over here? What's the area under this curve?
Is it also 1?
It's infinity. We just got this. It is infinity over here. Okay?
Right, yeah.
Right. Now, how come this one has a finite area 1, and then now here this is infinity? They kind of behave kind of similar, right? Like this, the curve, right? So you might wonder what happened. So what's happening over here, it is, as x go to infinity, this 1 over x squared will go to 0, right? And also 1 over x also go to 0, okay? Both of them go to 0. But 1 over x squared go to 0 fast enough, okay? Get closer to 0 fast enough. So then you have a finite area under the curve from 1 to infinity. This one here, 1 over x, doesn't go to 0 fast enough. So you don't have a finite area over here. So both of them go to 0, but this one over here, but not fast enough. So you might wonder, what do you mean fast enough, right? So how fast is fast enough, okay? So what does it have to do with the function? So that actually had to do with this exponent on this x over here, okay? This is x to the second, this is x to the first power, okay? Let's investigate what exponent over here is going to give you a finite area under the curve from 1 to infinity. So let's investigate this. 1 over x to the p power, and x go from 1 to infinity. And we want to find out for what value of this p is going to give you a finite integral over here. to make this integral convergent. Okay, so we ask, okay, now let's investigate this. Okay, so we have this integral. So we're going to express this by the definition, right? Remember, definition for improper integral. It's the limit of this proper integral. Replace infinity here by t, and then let t go to infinity. Right? So we have this t go to infinity. So what's the antideuty of this one here? You can rewrite this as x to the negative p power, right? Okay. So using the power rule, okay, so this is what's the antideuty x to the negative p will be x to the
negative p plus 1.
Negative p plus 1, right? And then divide by this exponent. So we're going to divide this by negative p plus 1. Okay, remember here, the x over here go from 1 to t. Now we're going to substitute. So this will be, so t to the 1 minus p, and then minus 1, and then over 1 minus p. So this is, this integral, this improper integral is equal to this limit over here. So this limit over here, if it's equal to a real number, if it exists, then this integral will be convergent, right? Okay, it will be finite. Take a look at this limit here. This limit here, if it exists as a real number, providing that t to the 1 over p limit of this part right here, it is a finite number because the rest over here are just constant, right? 1 and 1 minus p are constant. So it all depends on t to the 1 minus p. So if this limit here exists, then this whole thing here, the limit exists. So we're going to focus on this, the limit of this part right here. So take a look at this part right here. T go to infinity, and then t to the 1 minus p. Okay, do you guys remember? So what happened to this? Okay, let's just try to think about some example. Okay, t go to infinity of this t to the, say, 0.2 exponent. What does it equal to?
Is it infinity?
Yeah, that's going to go to positive infinity. So that's going to go to positive infinity. You see what happened over here? If this exponent over here, it is greater than 0, when t go to infinity, then t to this power will go to positive infinity. So it depends on this exponent over here. So it depends on this exponent 1 minus p over here. If 1 minus p is greater than 0, then when t go to infinity, t to the 1 minus p exponent will go to infinity. 1 minus p greater than 0, that's equivalent to p is less than 1, right? That means p it is less than 1. So what happened over here, we can write it down. So if p is less than 1, then what happened to this is this limit here will be infinity. Now what happens when you have limit as t go to infinity, say t to the negative power. T to the negative power, it is 1 over t to the third power, right? So when t go to infinity, then t to the power also go to infinity. So this whole thing here, the limit will be equal to,
It's gonna go to 0.
it's going to be 0, which is a finite number. So it sees it actually depends on this exponent, right? So if this exponent over here, it is less than 0, which means 1 minus p over here, it is less than 0, then what happens when t go to infinity, this limit here is going to go to 0. So, but 1 minus p less than 0, that's equivalent to p is greater than 1. So if p is greater than 1, so then this limit here will be equal to 0. So we have that. Now we can use this and use it back in this limit over here. So go back to that limit. So there are two cases. The first case here, it is if p is less than 1. The other one is if p it is greater than 1. Right? Now if p is less than 1, this part over here will be going to infinity. So this whole limit over here will go to infinity, okay? Or you can put down does not exist because this limit here does not exist. So, or you can put down infinity. Okay, if p is greater than 1, then this part here is going to go to 0. So what does this limit here become? So it's going to become 1 over p minus 1 because this is 0. Negative 1 over 1 minus p is equivalent to 1 over p minus 1. Now, after this investigation, let's write down the conclusion. When we have this integral 1 over x to the p power, when x goes from 1 to infinity, this improper integral is going to converge to 1 over p minus 1 if and only if, okay, IFF here means if and only if, p it is greater than 1. And it's going to diverge otherwise. What do you mean otherwise? Which means when p it is less than or equal to 1. So including 1. Remember when we integrate 1 over x, so the exponent it is 1, right? So you need to remember this conclusion. And that's the one that we're going to use again. Question? Okay, now let me see if you understand this. So let's take a look here. 1 over x to the 1.001 dx. X go from 1 to infinity. Convergent or divergent?
Divergent.
Did you say divergent or convergent?
Divergent.
Divergent? Okay, let's take a look here. It says that when p is greater than 1, then it converges. So what is the p over here? The p over here, it is 1.001, which is greater than 1. So convergent or divergent?
Convergent.
Convergent, right? So it is going to be convergent, actually converge. Okay, and we also can figure out what does it converge to. So it converts to 1 over p minus 1, right? So it converts to 1 over 1.001 subtracting 1. It converts to, remember this is the 1 over p minus 1, right? Okay, so that is equal to 1000. So if you try to find the area under the curve from 1 to infinity, that is going to turn out to be 1000. Now this one, 1 over x to the 0.999. Convergent or divergent? And x go from 1 to infinity. Convergent or divergent?
Divergent.
Yeah, it's going to be divergent. And it actually diverge to infinity. What about this one? 1 over x, but then it's to the first power, right? X go from 1 to infinity. Convergent or divergent?
Divergent.
So it actually also diverge to infinity. Okay, so that's improper integral of type 1. I'm going to stop here today. That's all for today. Okay. Do you guys have a question?